And it sort of matches what we talked about back in the Newton's law, F equals ma days. You know how in Newton's law we always say, oh, here's the basketball, and the weight acts at the center. We're basically saying that's its center of mass. Therefore, the weight acts at the center of mass. Therefore, if this force changes the momentum, it's all going to act like it's a point particle at the center of mass. We're really just saying the same thing. It's also true for collisions, because collisions are driven by the conservation of momentum. And the conservation of momentum is really the same as Newton's second law. Right? It's all the same thing. Okay? So, who cares, right? Why am I telling you this? Why? Oh yeah, we got to do this. Okay, let me show you why I'm telling you this real quick. Here we go, because this is a big homework hint. So let's take another derivative. Dr. Hafner, don't do it. No, I'm going to do it. Take another derivative. So we look here. Let's take derivative of this. What are we going to get? The acceleration of the center of mass equals 1 over m total, right, times what? m1a plus m2a plus blah, blah, blah. Dude, so then we bring this over here, and what do we have now? We have m total times a center of mass. We have basically what I just said, is you get basically Newton's second law, m1a1, with a twist, m2a2, right? So this is Newton's second. Sort of it is. It kind of is. Is it? So what am I missing to make that Newton's second law? Does anything look weird? It's very subtle what's weird. Let's think back to our isolated system. Let's apply this again to our isolated system, and then we'll talk about one in particular. Right, okay, so we got all this crazy stuff. I'm trying to convince you that center mass is important. We'll get to how we use it in a minute. But let's look at an isolated system with many components, say. And let's apply that and see what happens here. So what I would say is this is the sum of the forces part. Right? Sum of the forces equals, and then this is the total mass of the system. You add up all the masses, m total, times acceleration of the center of mass. So it's just saying that the system obeys Newton's second law, and it obeys it just like we said when we talked about Newton's laws. You can treat a big thing as a point particle. You can also treat a bunch of masses doing something together as a point particle. They don't have to be connected. Right? So we did Newton's second law. We said, oh, here's a bar. We'll put the weight down at the center. So here we're treating all the atoms that make up the bar as a system. But you can also just have a bunch of masses. So we'll show you in a minute. But what's missing here? What makes this not quite look like Newton's second law? They're supposed to be external there, right? The sum of the external forces equals mass times acceleration. So what about external? Well, if we say the sum of all forces, what does that mean? The sum of all the forces, that would be the external and the internal forces. Right? So if the system is being pushed by some imaginary, never mind. If the system is being pushed somehow, that would be an external force. But if there's little forces inside the system, those would be internal. But the internal forces cancel. Forces cancel. Due to whose third law? Yes, Newton's third law. For every force in the system, there's a reaction force. So that saves it. So you could actually write it, you don't have to say external, you can say all, if you're talking about the motion of the center of mass. All right? So you say, why do they teach it to us then why do we write external here? When we learn Newton's second law, it's because you're usually applying it to a single body. Right? So a single body can't have like an action-reaction force with itself. Right? You have to have at least two things to have an action-reaction force. So when you're talking about a system of a bunch of forces and a bunch of masses, you can bring in this idea that you can go ahead and mathematically put the internal forces in, because it's not going to matter, because they're all going to cancel, unless you miss one. And then, of course, then you're in trouble. Okay? Okay, so let's look at just one idea of how this works, and then I'll give you the big hint here. Let's see. Okay. So an example of this is the solar system. Let's think about the solar system. This is physics. I am a professor of physics and astronomy, so I'm about to tell you everything I know about astronomy. You ready? Here we go. The center of the solar system is the sun. I know that I don't know this for certain in sort of a philosophical sense. And then around the sun, we have Mercury. Oh, we don't want to line them up. That'll be like the end of days or something. So around here, we've got Venus going around here. And then we have Earth going around here. All right, there we go. That's all I care about the solar system. Once you get past Earth, does it really matter? No. I think Mars is next. Maybe Jupiter then? I don't know. So let's imagine now the solar system is drifting through space, right? So it's drifting at the velocity of the center of mass of the solar system. So where's the center of mass of the solar system? It's probably in the sun somewhere. I mean, this thing is so much more massive than these things, and these things are going around in circles. I guess if they all lined up, maybe the center mass would shift a little bit. I don't know if it would make it outside the sun or not. Probably not, although they are really far. So, what we want to look at is if this thing is isolated, what's the sum of the external forces? 0. Let's pretend there's no galactic center pulling us around. Let's imagine the solar system is just drifting. Okay. But then we know there's a lot of other forces going on, right? So this feels a force to the sun feels a force to that, and this feels a force to the sun feels a force to that, and the Earth feels a force to the sun, and the sun feels a force to the Earth. Oh, and shit, there's the moon going around. So the moon feels a force to the Earth, and the Earth feels a force to the moon. There's lots of internal forces, right? So don't we have to count all of them? Because we said every little MA, all has to add up. But you can see each one of these is a pair. So the sum of all the forces, of the internal forces, is still 0. So this thing is just drifting along, and all of its internal clockwork can keep going, and the forces can drive all the internal motions inside the system. But the system as a whole, its center of mass, is just moving along, right, as it goes along. So that's a case of a system that has internal interactions. That's gravity. There can be smaller ones, okay?